Alright, let's go ahead and continue with some continuity today. But we're going to take a look at like different worded or phrased questions that are still dealing with continuity that love to show up on AP questions or the AP test. Before we tackle those though, are there any homework problems that you guys want to go over? Hopefully we checked some last night. Yeah. From the last chapter? Or last section or something? Yeah. Go ahead. Number 14. Can you tell me page number? 51. Oh, yeah. Okay. Let's go ahead and take a look at 14. We're on page 51. If you plug in -1, what do you got?
0, 0.
0, 0. Okay, we have some more work to do. Okay, so what do you guys feel like doing? Can we factor anything? What do you think, Braden?
Can we turn the x plus 3 cubed into a cubic thing?
Yep, polynomial. Yep, expanded. Okay, we're going to get rid of all the parentheses. So this x plus 3 cubed, we'd have to write x plus 3 3 times and multiply all those together. So let's just multiply 2 of them together at once, going through like a FOIL or distribution process. X squared plus 3x plus another 3x would give us 6x, and then 3 times 3 would give us 9. But we have to take those two quantities now and distribute every term through. So x squared times x, we got x cubed. X squared times 3. Next we can bring in the 6x. And then lastly the 9. So combining some like terms, we have x cubed plus 9x squared plus 27x plus 27. Okay, that's if we expand just the x plus 3 cubed part. We then are subtracting 8 in the numerator, and we have an x plus 1 still in the denominator. We could probably go a little further here because 27 minus 8, that'll give us 19. I will give it to you. This one's a tricky one. Okay? Where do you guys want to go from there? If you try direct substitution again, okay, if you plug in -1 just to see if it would work now, I think you're still going to get 0 over 0, unfortunately. So we have to try some other techniques. Yeah.
Can we do synthetic division?
Ooh, why'd you do that? Good.
It's the only thing I thought.
It's the only thing you thought of. Okay, so hopefully some of us would probably think factor first, because I think we would prefer to factor over synthetic division. If you take a look at the numerator and you have 4 terms, you could try to factor by grouping. Hopefully we're familiar with that method. Now you could pull out an x squared from the first group, but between the 27 and the 19 there is no GCF you can factor out from there. And the only way factoring by grouping works is if your remaining factors, like after you pull something out, they match. So unfortunately there's no way we're going to get these two groups to match each other. So the division is factoring is not going to work out for us here. So we have to get around this somehow. And notice how we are essentially dividing, right? We have this whole thing divided by x plus 1. This one's tricky because I know it's not a technique we've talked about formally going through limits, but it is some type of algebraic process you could use. So when you think about actually dividing polynomials, I know last year you guys did long division, okay, but we also talked about synthetic division, kind of a shortcut way. If you are dividing by x plus 1, what would we put as that little kind of box or block number off to the side? Do we kind of remember how synthetic division works? Or maybe the setup? It's -1. Okay, so I'm going to do that. I'm going to do synthetic division down here. So -1 is a little block number because that's what makes your divisor equal 0. And then to fill in the rest of synthetic division, we're going to use the coefficients from the numerator, which would be 1, 9, 27, and 19. So refresher for synthetic division, we bring down the first coefficient. That number times the block number gives us -1. We write that underneath the next coefficient value, and then we're going to add those together, which would give us 8. And we're going to repeat the process. 8 times -1 is -8. Add to 27, we get 19. 19 times -1 is -19. Bless you. Add to 19, we get 0. Now that 0 is representing the remainder, since we are going through a division process. So since the remainder is 0, you know that this x plus 1 factor goes in evenly. Okay, there's nothing left over. What about this 1, 8, and 19 that we have left? What's that representing, or how can we rewrite those values? Go ahead, Braden.
X squared plus 8x plus 19.
Okay, so this 1, 8, and 19 are the coefficients on your quotient, okay, the answer you get from division. We would have the 19 represents a number, the 8 represents how many x's, the 1 represents how many x squareds. If we had more numbers, we would just continue with x cubed, x to the 4th, and keep going. So we have 1x squared, 8x plus 19. Okay, so that's your quotient value. And if you were to take the quotient times that divisor, x plus 1, you would get your original polynomial or numerator back. So we can use synthetic division as another option to help us factor, even though grouping didn't work. You really had to dig deep for that one. Do you think we can go from there? Do you notice anything that's going to happen? You see the x plus 1s are going to go away now? Right? So with your leftover quadratic equation there, go ahead and plug in -1 and see what your limit would be. Is that okay, Allison? Okay. Any other ones you guys want to check out, either from the last section or the continuity from yesterday?
What's the answer?
Oh, I don't know. I wanted you guys to do it. If you plug it, let's see, if you plug in -1, this would be 1 minus 8, so -7, plus 17, you get 12.
Yeah.
Okay. Anything else you guys want to discuss? Yeah.
I didn't know how to do 12.
12 above that one?
Yeah.
Okay. Let's check out 12. Okay. It would help if you guys could see it. If you plug in 0, well, let's try it. If we plug in 0, tangent of 0, okay, we're thinking about the beginning point on the right over there, which is 1, 0. So if we did tangent, we would need the sine divided by the x, or cosine. So 0 divided by 1 is 0, right? And then down below, the sine value of 0 is 0, and the cosine value at 0 is 1. So 1 over -1.
Oh, wow.
Direct substitution worked. So you didn't have to use any fancy trig limits or factoring or anything else. That's why you always try it first. Plug it in. Any other ones? All right, let's go ahead and check out page 55. Okay, back to this continuity idea here. So let's kind of refresh our memory. We formally defined continuity yesterday. Okay, you can think about it as no holes, no jumps, no asymptotes. You can think about it as being able to draw a graph without lifting up your pencil. Okay, but there are three things mathematically that have to be happening in order for a graph to be continuous. Can we name any of those three? Think about our little driving or river bridge example. We have three conditions for continuity. Yeah. There has to be a point, aka you have a bridge. Yeah. There has to be a limit, aka you have a road, like coming in on both sides. Yeah? You need the point and the limit, the answers from those to match, meaning the bridge and the road meet up so you can safely cross the river. Okay? So we're going to use that definition again today to help us look at these different worded type questions. So off to the right, we have this piecewise function. The first question is asking us what two limits must be equal in order for this piecewise function to be continuous at -1. Now, if you look at the piecewise function, notice how -1 is a part of that kind of domain or constraint area. -1 is where your first function is ending, but it's also where the second function is beginning. So in terms of continuity, if one function is ending at -1, whereas the other one's beginning at -1, we need to make sure that they begin and end at the same place. That way you can continuously draw your graph. If they don't end in the same place, we realize we're going to have some type of jump going on. Okay? So what two limits? Can we write out that mathematically? What two limits must be equal? Remember, the second piece of our definition is that the limit must exist. Thank you. So what two limits must equal in order for an overall limit to exist? Yeah? -1 from the left and -1 from the right. Okay, so let's write that out. The limit from, or x approaching -1 from the left must equal the limit as x approaches -1 from the right. Okay, now in terms of notation, a limit always has basically three pieces. You have the LIM, you have the value of x that you're approaching, but then you also have to write the function. Now sometimes you see f of x there, but sometimes you also might see an expression there, like in most of your homework examples. So what expression or equation can we write in here based off of this piecewise function that represents the left-hand side of -1? Can we pick which one of these three pieces shows up to the left? Good, Braden? 2. Okay, so let's go ahead and use the 2 function to represent the left-handed side, and then which function would represent the right-handed side of -1? Yeah. The mx plus k. Okay, the second one. Good. Right? How about a very similar question for part B? What two limits must equal in order for the piecewise function to be continuous at 3? So we have to check what's going on to the left of 3, but also what's going on to the right of 3. Those must equal in order for the overall limit to exist, which is a stipulation for continuity. So of the 3 equations, which one shows up to the left of 3? Kind of values just below 3. Good, Braden? The mx plus k, which means to the right of 3 looks like we have that -2 value. Are we okay with that setup? Okay, based off of the way the piecewise function looks? Okay? So if these limits must equal in order to be continuous at -1, and these limits must equal in order for us to be continuous at 3, okay, let's try to answer this question. Do we know if the point exists at -1? Can you tell based off of the way the piecewise function looks? Yeah.
The piece should exist at -1.
How do you know?
Because x is greater than or equal to -1.
Okay, you see that bar there? The fact that you can plug in -1 means that you have a point. So the point already exists at -1. Okay, we know that's 2 actually. And we also know the point exists at 3 because we get -2. So we already know the point exists for both of those. We need to check, does the limit exist for both of those? And then we can determine like if it's continuous or not. But in order to be continuous, the limit must exist because that's one of the stipulations, one of the 3. So let's go ahead, and with these 2 equations we have set up here, we're going to try to figure out what is that value for m and that value for k in that second equation that would make the function continuous everywhere. -1 and 3 are the only values that are of interest because that's where the pieces end and begin. Okay, we want to make sure that they meet up because again, if they're not, we have that jump going on. Okay, so let's go ahead and take a look at this first equation we have here. What's our first step in a limit? What do we do? Substitute it in, right? If you tried to plug in -1 into this first limit, notice how there's no x value to actually plug it into. So the only answer you would get out is 2. Okay, this value of 2 is not going to change. There's no variable there to change it. Remember, variable means change. So I guess the simplification of the left-hand side of this equation is 2. Let's go ahead and simplify the right-hand side, this other limit. If you were to plug in -1, okay, just for the x value, notice how we would have -m plus k, right? So this equation is representing the limit at -1. Let's go ahead and do the same thing for the limit at 3. If you were to plug in 3 just for the x, you would have 3m plus k on the left. And if you tried to plug in 3 for the right limit, you would only ever have -2. So if our goal is to figure out what is m and what is k, and we now have these 2 equations to possibly utilize, what can we do with those 2 equations to eventually figure out m and k? What are some techniques or algebraic steps that you can use to figure out m and k? What do you think, Vinny? Alright, so we can use a process called substitution. Okay, we have a system of equations here. I'm pretty sure you guys have heard that vocab before, system of equations, 2 variables, 2 equations. We have 2 techniques you could try. Substitution is one of them. Elimination is the other. Sometimes I prefer that one. So we'll actually go over both, but we should be able to get the same solutions either way. Alright, so Vinny discussed the substitution route. Which variable in that first equation did you want to solve for again? You want to get k by itself. Okay, so if we take the first equation and add over the m, we'd have 2 plus m equals k. Now, Vinny, do you want to keep going from there? What would you do next? Okay, so if k equals 2m, we can take that 2m and plug it in for the k in the other equation, okay, the one we didn't use yet. So that would be 3m plus 2 plus m would equal -2. Okay, if we plug it in for that k. So now we kind of merge the 2 equations together and we have one equation with one variable. Let's go ahead and solve for m. 4m plus 2 equals negative 2. You can subtract the 2 over. So it looks like m is 1. We've done substitution before, right?
Yes.
Yeah? Did I do something wrong? Is that checking out?
Yes.
Yeah?
No, it's you turn the
Oh, M is negative 1.
Oh, this should be a positive 4. I'm sorry. So this is negative 1. I saw faces on some of you, like what's going on. So that's usually my hint that I did something wrong.
I was looking at a K.
Okay.
Which should be 1.
M negative 1, that's better? Okay. So now that we know what M is, how can we figure out K? Because again, we had 2 values to figure out. What do you think, Braden?
plug m into that equation later.
Okay, so you can pick either equation you want that you started with. We're going to plug in negative 1 into the m position. It doesn't matter which one you pick. I think the first one's a little easier. If we plug in negative 1, this negative would change it to a positive 1. So then subtracting the 1 over, we would get a k value of 1. Alright, so bringing back those algebra skills, systems of equations, so we can go the substitution route if that's what you see first. Are we familiar with elimination? Maybe some of you prefer that. You have to have a particular setup though first for elimination. Do you know what that looks like? There's kind of like an organization to it. Okay, what we're going to do is we're going to take these 2 equations and line up every variable and number appropriately. So if we want to keep this equation the same, for instance, 2 equals negative m plus k, we need the number value from the other equation underneath this one. So notice how that would be the negative 2, and then the equal sign. We're going to line up the m's, so we have a 3m here, and then we're going to line up the k's, which would be a plus k. You may have to do some rearranging. Sometimes you may have to move terms to the left and right, but you want to have that organization to it. Line up the k's, line up the m's, line up the numbers, line up the equal signs. Okay? So in the elimination process here, we're trying to get the coefficients in front of either variable to kind of be the same number. That way we can either add these equations together or subtract them to literally eliminate a variable. Now what's nice about this setup is notice how the coefficients in front of the k's are both 1, right? If they weren't, we would have to multiply everything by something. Is that coming back to us a little bit? Okay, so but they match, no issue there. So in order for us to eliminate k, we would have to take this 1k and subtract the other 1k. So we're going to subtract these 2 equations together. And just working through, we would have 2 minus negative 2, which would end up being 4. Negative 1m minus 3 would be a negative 4m. And notice how 1k minus another 1k would eliminate that variable. So now that we have this resulting equation, you can divide over that negative 4, and you still get the same m value from the substitution work, right? Okay, so at this point, you can pick either equation again to plug in the negative 1 for m to figure out the k value, so we would still get 1. Okay, so it's whatever process you're more familiar with or comfortable with. Whenever you have a system, we're either going to go the substitution or elimination route. Okay? So those are the values for m and k that would make the function continuous. So this equation in here would have to be negative x plus 1, okay, the m and the k, in order for every single piece to end and meet at the same spot. Okay, that's what we're checking. No jumps, no holes, no nothing happening. Yeah.
I calculated m a bit differently.
How'd you do it?
I looked at where the 2 points, it basically ended at like -1 on the x, it ended at 2, and 3, it ended at -2, and that was the vertical distance was -4.
Okay.
And I found that along the -1 and 3, that is also a horizontal distance of 4, which you would need to have a slope of 1
Okay.
in order to do that.
So you looked at it in a graphical sense
Yes.
instead of algebraic. That would work too. Okay, that would work as well. All right, let's go ahead and try another one on the back. Very similar process. Okay, consider the function g of x to the right. What two limits must equal in order for your graph to be continuous at -2? Okay, if you take a look at the piecewise function, we already know the point exists at -2 because we have that bar there in the second domain. So we already know the point exists. Now we have to make sure that the overall limit exists. And this is where it gets tricky with the piecewise functions because you have multiple sections from the left and the right to check. Alright, so let's go ahead and see the limit from the left of -2 must equal the limit from the right of -2. Can we fill in the function or expression pieces appropriately? Which piece shows up to the left of -2? Which one shows up to the right? Are we thinking kx squared plus m for the left side? Okay. And then 4x plus 1 for the right? Let's write another limit equation. This time we're going to check the continuity at 3. So we got to figure out what's happening on the left of 3 and what's happening on the right of 3. Again, we know the point exists at 3 because we have that bar. So it's already satisfying that first condition for continuity. We just need to check the limit now. So we'll fill in the left and right equations. Are we okay with that setup? Okay. So now that we have those two equations, we can use those to help us figure out, well, what number should m be and what number should k be in order for every single piece to end and meet at the same point. Okay, so looking at the first equation, we're dealing with limits. You always plug in that number first. If you plug in -2 for x, we'd have -2 squared, which would be 4. And if we plug in -2 for the right-handed limit, we'd have -8 plus 1, which is -7. So there's one equation we're going to utilize. Let's take a look at the other one. If we plug in 3 on the left-hand side, we'll get 13. And if we plug in 3 on the right-hand side for x, we'll have 3k minus m. Alright, two equations, two variables, and they want us to solve for those variables. Do we want to try substitution? Do you want to do elimination? I could do both. Just want to see if we have a preference. You want to try elimination? I saw a substitution back there. Okay, how about you guys do you? Okay, you do what you're most comfortable with, and we'll check our answers. Because regardless, we should all get the same results. Okay, so you do you. Myself, I'm kind of an elimination person. Some days I'm substitution, just depends on my mood. How do we do with the fractions? Good. Can get tricky. Okay, so substitution people or elimination people, we should either have, or we should have both gotten the same thing. How do we do? Do we need to go over any step, any process? I did elimination, but I can easily erase and do substitution. Do we want to see it the other way? Maybe? Okay, so that was elimination. If you set it up in your organized columns, the m's had the same coefficient, okay, 1 and 1 happens to be -1. So to cancel those out, we could add them together. Notice how the m's would go away. So k would be 6/7, and then pick any equation you want to plug it into to figure out m. Okay, let's check out substitution. For those of you that did substitution, how did you start? Did you pick an equation? Which variable did you solve for? Shouldn't matter. Yeah. Okay, so you subtracted the 4k over. So let's take -7 minus 4k, and we're going to plug it in to that m. Now what's tricky with this is you are subtracting m, so you have to subtract all of that you're plugging in, because we'd have to distribute that negative through, which would affect all the signs. So it looks like we have 7k plus 7. Subtract the 7 over, we'd get 6. Divide the 7, we get the 6/7. Okay, same k value from before. Okay, so pick either equation you want. Maybe we'll plug it into this one this time. 4 times 6/7 plus m. We got 24/7. We'd have to subtract that over. But we have fraction work, so common denominator, this would be -49/7. And -49 minus 24 gives us that -73 again. So we get the same m value. Substitution, elimination doesn't matter. You do you. We doing okay? Alright. So the last few problems on that homework for this section deal with that elimination or substitution process. Okay, trying to figure out where a piecewise function is continuous, or for what specific values it should be continuous for. Okay, so it's a very similar kind of repetitive process. It just depends on the piecewise function you have. Okay, we still have about 5 minutes or so left if you want to try some of them. If not, you guys have a good weekend. Okay.